Welcome everyone to another session of the Ken Seminar Series, Spring 2025. We're excited to have you all join us today, and it's our absolute pleasure to host Professor Sayan Mitra in this session. Professor Mitra is a faculty member in the Electrical and Computer Engineering Department, ECE, at the University of Illinois Urbana-Champaign. His research focuses on reliable autonomous systems, and his group develops design and analysis software for autonomous technologies. His former PhD students include faculty members at MIT, Vanderbilt, Washington University in St. Louis, and the University of North Carolina. He earned his PhD from the Massachusetts Institute of Technology under Nancy Lynch, and his textbook on cyber-physical systems verification was published in 2021. So please help me welcome Professor Sayan Mitra.
Okay, good afternoon. Thank you very much for the kind introduction. And thank you for having me here today. I was fascinated to learn about the work that you all are doing here, very important work, different from the work that I do, but it was a wonderful afternoon. So thank you very much. This talk is going to be about autonomous systems and applications of autonomous systems in transportation. And I'll touch upon some work that we are doing in designing reliable autonomous systems. So I'll begin this talk by describing some sort of general perspectives on where I think autonomy is, where the exciting things are happening, what the challenges are, and then I'll give you a couple of snapshots of the research that I've been doing in the last few years. So I would say autonomy is having an inflection point in transportation, and the changes that we are seeing are quite disruptive. So if you look at autonomous flight, within 100 years of controlled powered flight on Earth, we are doing the same in Mars. This is the NASA Ingenuity helicopters that flew in 2021. Considering that there was no flying going on anywhere 100 years ago, I would say this is a pretty fast change. And it's happening because of autonomy. The Mars thing could not have happened by manual control. Same goes for flying cars. Many of you probably know that there is a plan for having an air shuttle between O'Hare and Chicago by this company, Archer. It's supposed to happen in the next 3-4 years. The technology for flight has been around for a long time, but autonomous flight at the level of small aerial vehicles for transportation without necessarily having trained pilots, this can only happen if you have strong autonomy on board to assure there is no collision and safe landing. Similar story for ground transportation. 1950s, 32% of Americans had cars. This year, I think we crossed a threshold where the largest share of taxis are autonomous in the city of San Francisco. So 22% of the taxi rides are by Waymo, completely autonomous, which is larger than the next highest share, which is by human-driven Lyft taxis. So things are changing pretty in some interesting directions, and it's quite exciting what autonomy can bring us. Overall, I think it can be a very positive thing for society. Just talking about cars for a moment, Americans drive something like 300 hours every year, which is like a whole summer vacation's worth of time in driving. So if you didn't have to do that, you can become more productive. Our cities can become greener. Maybe we can solve this urban housing problem because cars can drop you off where you need to be, and then they can go and park somewhere else, and doesn't have to take up large parts of city spaces. But all this can happen provided autonomy is reliable. And it's obvious, I don't have to repeat this. If you're reading the news, you see, like, for air traffic in particular, even for trained pilots, it's a very challenging problem, air traffic management. The national airspace is an aging system. So integrating autonomous flight in that is going to be exceptionally challenging. And it is also the case for road traffic. Despite all these advanced features that we are having on driver assist systems and autonomous driving systems, the number of traffic deaths in US is actually not decreasing. It has sort of stabilized, and in the last couple of years after the pandemic, it has increased a little bit, actually. There are various different theories for that. So autonomy has to be reliable and safe for us to reap all these benefits that we hope to have. So here's a snapshot of where things are, comparing autonomous driving with human driving. So this is a chart I took from this recent paper that appeared in Nature Communications. And this is giving you the fraction of accidents, road accidents, in human-driven cars. So there are 35,000 accidents that have been analyzed. And the authors have categorized them in terms of what was happening before the accident, what kind of environment the car was driving in, as well as what was the type of the accident. For example, out of these 35,000 accidents, 45% were rear-end accidents. Okay, and these are for human-driven cars. 32% were head-on accidents, and so forth. So that's the picture for human-driven cars. Now, for autonomous cars, this is the comparison. The first point to note is the amount of data we have is much lower, right? So there are fewer cars being driven autonomously right now, and even fewer number of accidents. So it's like really low data regime. 1,000 or so accidents have been analyzed. And you can then start to see how these two charts compare with each other. In many cases, actually, you see the accidents are sort of parallel in terms of percentage-wise. The number of accidents in daylight in both cases are comparable, roughly. There are a few outliers. For example, inattention happens to be, as expected, a large percentage of causes or at least correlated events that happen for human accidents, and there is no inattention for autonomous cars, obviously, or at least not for now. Then there is another discrepancy between pedestrians involved in accidents. So for humans, that happens to be a large percentage, 15% or so of these accidents involve pedestrians, whereas for autonomous cars, it's only 5%. Also sort of makes sense because there has been a lot of attention in detecting and avoiding pedestrians in the context of developing autonomous cars. Okay, so that's where things are. My take is that we are sort of in a fork in the road. This phrase has become quite overused these days. So we will see how things go, okay? The technology has improved a lot, for sure. These are really capable systems that Waymo has and Tesla has and so forth. Numbers, we don't have yet enough data to say how the two compare. It's promising, but it's not 100% clear that we are going to achieve acceptable levels of reliability in the near term. And one of the challenges is actually the way we are developing autonomous cars and testing autonomous cars itself is limited. And this takes me to the second part of the talk that I want to get to. This is a famous saying in computer science from Dijkstra. It said basically, if you test a system, you can find bugs. But if you test the system and don't find bugs, that doesn't mean there is no bug, right? So testing can show the presence of something, but testing can never show the absence of something. Showing the absence of something is very hard. How do you prove something does not exist? Like a bug does not exist, or a bad design does not exist. Just a fundamental limit in how we think about systems. And testing alone cannot be the full story. And so going beyond this sort of argument, you can even do the basic statistics of testing for autonomous cars. And these people have shown that it's actually prohibitive. The amount of testing that you have to do to make a claim about reliability is just not feasible. Let me sketch for you the rough argument. The probability of a fatal accident for human driving is roughly 10 to the minus 6. For every hour of human driving, the probability of having a fatal accident is 10 to the minus 6. Okay, this is US data. So one can argue to have autonomous cars accepted by society, the probability of fatal accident per hour has to be 3 orders of magnitudes better. Okay, and this can be substantiated by some other records from FDA and other safety critical systems. So an autonomous car has to have can only have an accident probability of 10 to the minus 9 per hour of driving. Okay. So if you want to make that kind of a claim, 10 to the minus 9 probability, then you need to collect data for at least 10 to the 9 hours to see the first accident, right? And that roughly means 30 billion miles of driving. Okay. Autonomous driving companies now are driving roughly 40 million miles, 50 million miles per year, and they're losing $1 billion a year. Okay. So the way things are going, you're not going to have enough miles to even make a statistical claim about safety. Okay, you're going to run out of money before that happens. Now, of course, non-technical reasons can come in, like political or economics or legal. You might be able to get away with it and just drive things that are not rationally safe, but people accept it, right? But if you wanted to be sure and have a high level of confidence in these systems, then this may not be the full story, just testing. And if you put on top of that other complications, like, oh, this is an open system, human beings are involved in driving or managing the system, there is a gap between simulation and testing, or every time you do a software update, you might have to retest the whole system because potentially it's a different system now, right? Then I think this approach clearly is not going to be the full story. Okay, so that brings us to what one of the main points of my talk, which is we have to somehow combine statistical reasoning and testing, which is very important, with formal or more mathematical reasoning about systems. So you all have experience with some level of mathematical reasoning about system in different contexts. Let me reach a common ground by just keeping in mind proofs of geometry that you did in high school or college, right? So that's what I mean by mathematical reasoning. A proof contains more than 1,000 data points, right? So I can give you examples of many Pythagorean triples, right? 3, 4, and 5, and so on. But instead of giving you all these examples, I could just give you the Pythagoras theorem, and that tells you exactly what is the relationship between two sides of a rectangular, right angular triangle, right? And we want to take that approach also in reasoning about autonomous systems. And this is the field of computer science called formal verification. It's the science or art of proving or disproving statements which are asserting correctness of systems. Okay? A statement about correctness of a system. We are not proving statements about geometric objects like in Euclid's geometry, but we are talking about the behaviors of a system, like an autonomous car. And it's not a figment of our imagination that you can do rigorous proofs for autonomous cars. Actually, this kind of formal verification is being used in the industry at a very large scale. For example, in Amazon, the software companies, Meta and Microsoft, engineers, not just researchers, when they're developing software, in addition to testing, they're often actually proving a theorem about the correctness of their software. This is happening today. Thousands of software engineers are actually also using theorems and proofs to assure that their software has the right property. For example, in Amazon, people are using AWS for building all kinds of services. And they care about security, like one person's password does not leak or one person's private information does not leak into another person. So they are using this type of tools to check correctness of cryptographic protocols and network protocols and so forth. This is happening today. So what we would like to have is similar tools and support for building autonomous cars, where an autonomy engineer who is developing, let's say, the next generation adaptive cruise control system or the lane keeping system or the software for an EV, they can also use mathematical proofs to show that the system behaves correctly. Okay, that's what we would like to build. So here is sort of like the dream of how this is going to work, and I'll give you some snippets of the kinds of things we can do now. So this is an engineer. They're developing some code, and there is also some database. These are the models of cars and tires and what have you to do the analysis. There might be some machine learning models, which we will talk about later, which is doing the perception, detecting the lanes from the camera images. So all of that together describes the model of the system, okay? And in addition, you also have the specifications of the system. Specifications are statements about what the system should be doing. For example, the car should stay inside the lane. That then goes into what I'm calling a verification engine. Think of it as a compiler. But in addition to just generating code, it can actually prove those theorems from the previous slide. And ideally, what this verification engine will do is either give you a certificate which says, oh, in all kinds of conditions that you care about, like such and such friction of the road and such lighting condition, the car indeed stays inside the lane, right? It gives you a proof of that statement, whatever a proof means. And that kind of a proof can be reassuring to the public, and it can also be a mechanism for satisfying federal agencies like NHTSA, who are ultimately giving you the safety certificate that, oh, this is a safe machine, right? So it can generate these proofs, or it can generate a counterexample saying, no, here is a particular road curvature and a lighting condition and speed in which the car actually does not stay inside the lane. Here is how it veers off the lane, right? So that's a counterexample. The proof didn't go through, but that's also pretty useful, right? Then you can go and try to debug your system or say, okay, maybe we shouldn't design lane markers like this. So that's the overall sort of development framework that we would like to have, sort of in parallel, like what is already happening in the software industry. And one important thing is this whole feedback thing has to happen in like very fast, right? 15 minutes. By the time you say, go check my system, you go for a coffee, you come back, it has either given you a proof or it has produced a counterexample. And then you can go and improve your stuff. So this is the kind of thing we are building. My research is mainly on creating such verification engines. Very quickly, I'll tell you about a couple of examples. So here is a description of an autonomous drone that is trying to avoid another drone in one of the software tools that we are developing. Okay, so inside of how this tool works, there's a lot of interesting math, and that's what we have been working on for the last, I don't know, 10 years or so. But this is the final user-facing side of it. This is how a user would use the tool. So this little Python-like code is describing the interaction between these two drones. So this drone, as it comes close to this other drone, it has a choice of either avoiding it by going up or down. And that choice is written out in this kind of a logic here. It's called a decision logic, which shows that if the distance between the drones fall below a certain distance, then it can either move up or it can move down, right? Sort of like a very simple adaptive cruise control or a passing maneuver that the drone can do. So that's part of the description of the system. Then there is sort of the overall scenario in which, say, there are two drones, and my overall scene has this map, which is describing what the lane geometries are, in this case, in 3D. And then you can say, go and verify, right? This is the line of the code which is calling that verification engine I was telling you about, right? When you do this verify, then all these algorithms and stuff that we've been working on comes to life, and then it does the analysis. And in this case, the analysis is called reachability analysis, which computes all the possible behaviors of the two drones that are running this logic from the previous slide. Okay. So you can visualize and then look at the results from this analysis. And one of the things that can come out is a visualization like this, which actually shows all the possible position that the drones could have occupied in a certain finite amount of time, starting from a set of initial conditions. So the red one is the drone behind, and the blue one is the drone below. And you see these are the possible areas that they could have been in. And in this case, because they don't overlap at the same time, you can infer that the drones did not collide. Okay. You can also potentially find counterexamples this way. Okay, so that's one snapshot I wanted to share. And this tool has been applied to do various different kinds of analysis. So for example, these air traffic management protocols are getting pretty complicated. Some of them also use machine learning. And so this was a study done at NASA by one of my students who's exploring one of these new traffic avoidance protocols for UAVs. So this blue one is an intruder UAV, and then the red one is the ego ship, the UAV running the avoidance protocol. And these different branches are showing what are the different ways in which the UAV could have avoided the protocol, avoided the intruder, and which of these are safe and which ones are not safe. And these are similar analysis for drones as well as multiple cars, autonomous cars potentially, that are going through an intersection. And again, you can try to check whether this six-way intersection is being negotiated safely by these cars or not. Yeah, these are some more examples of collision avoidance in 3D by aircraft and so forth. Okay, so that's one of the sort of things, reachability analysis from code that is describing the behavior of interacting agents, potentially including a nonlinear physics describing the actual motion of the vehicles. The next piece I wanted to talk about is the role of machine learning in autonomous cars or autonomous vehicles. So this is a footage of airplane landing. So it's work that we are doing with Boeing on automated landing using cameras. So you see the camera is detecting certain key points on the runway. And from those key points, the pose of the aircraft is being estimated and then do the automated landing. Okay. All right, so if you look at this pipeline for automated landing, here is what it looks like. So there is a runway, that's the image. This is being analyzed by a neural network to detect those key points on the runway. And then there is geometric calculation that is happening to estimate the relative pose of the aircraft with respect to the runway. And then there is a controller which decides how to fly the plane given the relative pose. Okay, so this is the pipeline that you would like to do similar analysis like we saw earlier. But the challenge here is this part of the system where you are working with an image and you're trying to do pose estimation, we don't have a very good handle on it. The neural networks are pretty complicated. The image generation process also depends on various factors like lighting and so forth. So we really need to understand what are the conditions under which we can even hope to give some sort of a safety assurance. And that is called this design domain problem. How do you figure out what is the operating design domain of the system in which we can give a safety assurance? And it's not unique to airplane landing. Here are some other experiments we are doing in the lab. I wanted to make this point that deep learning is already showing up in many different parts of the autonomous system. So these are drones that we are using to do some sort of racing kind of tasks in the lab. So this is one space where we are going to do experiments. And what is interesting in this video is actually this is not a regular video captured from a phone or anything. This is created using what is called a neural radiance field. So from images, you can construct a 3D model of the space which is represented by a neural network, right? And then you can query that representation from any position and say, what does the image look like from that position? So it's not like the traditional computer game type of environment with lots of polygons. It's a neural network representation of the space. And what is nice about that is it's completely data-driven. Just from camera images, you can construct this. And then you can learn policies for controlling the drone or the airplane in that environment. So that's what we are doing. So we have created these different representations in neural networks. And on that, then we train our control policies. So that's the NERF representation of the space. And this is the actual drone flying in that space. So it's pretty close to what the NERF is seeing. And this is the experiment of actually flying the drone through the gates using the learned policy. Anyway, the point I'm trying to make is this deep learning is a superpower for autonomy. You can create these environments just from data, and you can also train these policies by writing a loss function. But the tricky part is you cannot really always trust what is coming out of deep learning. So, okay. All right. Yeah, so while it's very convenient, it is often unreliable, right? You cannot really say when the output from a deep learning function is doing what it is supposed to do. So for example, here, again, going back to the vision-based landing system, we are using this neural network to detect the key points. And as you see, if we change the lighting on the runway, the key point detection is all over the place. And from that, the pose estimation is going to be all over the place. And the overall system is not going to work, okay? And here, what we are changing is the ambient lighting and the position of the sun. But otherwise, everything is the same. The pose of the aircraft is still the same. So we want to do analysis of these types of systems with neural networks in the pipeline. And we have I'm going to skip some of these detailed definition. We have a technique that we are calling perception contracts. Yeah. So a perception contract is a way to over-approximate what the vision pipeline is doing with the neural network so that you can still prove the correctness of the system, like the safety of the system. So in a nutshell, if your original vision pipeline was taking a state of the airplane, so X here is the actual state of the airplane, like the position, the pitch, roll, and yaw, and all of that. And from that, it was generating an image, right? The actual view of the runway. And that was being used by the controller. Now, what we are going to do is going to replace this observation of the system with an over approximation, which is not going to give me the image, but it will going to give me the set of possible estimates that could have come from that image, pose estimates. And if we can construct this over approximation of what the neural network is doing properly, then we can prove correctness of the overall system. So that's the idea. Again, so if you can do this, then you can get some end-to-end safety properties. Today I will not get into how exactly we construct this over approximation. But the method for using it is as follows, right? So you will have to collect some data. So for example, here, one of my former students is seen flying this drone in the lab where we do experiments. And we are also collecting the actual view of the landing pad as seen by the drone. So we collect these data pairs of the output image from the drone's camera as well as the ground truth information. And based on these pairs, we solve an optimization problem that finds the best possible over approximation that fits the data. And it can also prove this safety property that we care about. So it's like a joint optimization problem or an empirical risk minimization problem for those of you who have seen this type of problem. So anyway, the net effect is out of that, we get this m theta, which is this perception contract that we care about. And with that, then we can prove this end-to-end safety property that indeed, these are the conditions under which the airplane can stay within the safe cone and achieve the landing. All right, so just to finish this part, here is the kind of analysis you can do. What comes out of this analysis is, okay, the environment that we care about here is the position of the sun and the ambient light. You could have many other high-dimensional environmental parameters. And out of all the possible combination of values, this green zone, this is the area in which our engine could find an appropriate over approximation or a contract, the m theta from the previous slide, such that the end-to-end system is safe. And this picture is showing the set of reachable states that the airplane will be in, which shows that it is going down to the runway in a safe way. Okay. In this case, the analysis shows that the system is safe in some set of lighting conditions. If you're not happy with this analysis, then you can also constrain the environmental conditions some more, but say, okay, I want to make the lighting conditions more favorable to the autonomous system, and maybe I can prove a stronger property. Maybe it can land from a larger set of initial conditions or with a larger set of velocities. So you can do this kind of analysis as well. Okay, so I think I'm almost out of time. So I'll just summarize the findings of what I wanted to emphasize today. So first is, combining formal and statistical reasoning provides us a way forward to get a high level of assurance for these autonomous systems. Testing alone is probably not going to be enough. So we have to combine statistics or testing with model-based, symbolic, formal. These are all interchangeable words. Formal reasoning about the system. In the first part of the talk, I was talking about reachability analysis, where the formal reasoning was coming from the logic of how the different agents make decisions. And the statistics was coming from the physics of the individual vehicles. In the second part of the talk, the formal part was coming from the architecture of the overall system, the fact that you have a perception pipeline followed by a controller, followed by plant dynamics. So we are exploiting that formally. And the statistics was coming from collecting the data about the perception pipeline, because that part, we don't yet know how to completely handle it formally. So we introduced two sort of snippets of ideas, just an introduction, reachability analysis, and this idea of perception contracts, the second part. So maybe a higher level takeaway is, use deep learning. It's a very powerful tool, cannot ignore it anymore if you're working on autonomy, but you have to also learn to verify things. That is a skill that is going to continue to be important, how to check correctness of answers, because these systems can often produce things that look okay, but may not be, right? All right, so that's all I wanted to share with you. Thank you for your attention. Question from online, or maybe we can take questions from the room.
Start by questions from the room.
Okay.
So whoever asks a question, please raise your hand.
Thank you, Professor, for the presentation. I really enjoyed it. I just had a silly question about, because you were showing a very simple logic for when the two drones are meeting, like either go up or go down. And then later on, you showed another example of an intruder object and an ego object. And it seems that this logic was only for the ego
Right. Yeah.
aircraft or something.
Yeah.
So I was wondering, because we're trying to optimize this and find like the best policies, if both of them are automated and both of them have the same logic, then that's a problem.
Potentially, usually there is some symmetry breaking built in to this type of logic. And in the extreme case, you can use your own ID to say, okay, the one with the lower ID has some priority so that you don't get into some sort of a, loop or a deadlock or something like that. Usually there is some symmetry breaking built into it. But if you want to, it can become theoretically very interesting. If you relax some of those assumptions, you get into game theory, for example, pursuer evader games. On the more practical side, just being able to do this for one agent, which has the logic, and the other agent, which is sort of just passively flying, maybe not even doing something active collision. That's where things are. Like if we can test those types of systems are safe and we can deploy them, that's already cutting edge, I would say. Because it's a pretty high dimensional system. There are lots of scenarios that can arise very quickly. Yeah.
Thanks for the very nice presentation, Professor. So you mentioned in a slide where like you substituted, I have no background on this, deep learning with over assumption. I didn't understand the term over assumption.
Over approximation. Yeah, let me go into that. I rushed through that a little bit. Yes, so the idea is ultimately this whole box over here, right, which is taking a state and then it is generating an image given the state of the airplane, which is some position and orientation. It is looking at the runway. It generates an image And from that image, deep learning is generating an estimate of where the airplane is, right? That's the whole role of deep learning in this particular problem, right? But ultimately, it's a function. It's a function which takes the state and gives you an estimate of where the state is. And what this over-approximation is doing is trying to over-approximate the behavior of that function, okay? So it's literally this. If you think of the x-axis over here as the actual state and the y-axis as the estimated state, then the deep learning based system is the line over here, right? It's some function. It can be very complicated function, right? It's a line saying, oh, if I'm close to the runway, my estimates are pretty good. Maybe it's actually equal to the actual state. If I'm very far from the runway, maybe my estimates have a bias, so it's a little bit off, right? So, but that's the purple line. It's a function. Whereas an over approximation is going to be not a line, but a range. So it's going to capture the variations in that function that can arise even with changes in lighting or other parameters like fog or what have you, right? So that's what I mean by an over approximation. Yeah.
So that is the confidence interval based on.
Correct. Yeah.
Thank you.
Any other question? I have a couple of questions from Professor Reisler. So the first one is, what sensors are used on a drone to detect the other UAV that was on a collision trajectory? And how do you deal with the second drone decision matrix?
Okay, so actually I talked about drones in a couple of different contexts. So for the UAVs that are being considered for this flight in open spaces, deliveries, the protocol is called ACAS-XU. That's the collision avoidance protocol that I was referring to and that we have studied. Which sensor is used to estimate the relative pose of the UAVs? Actually, the protocol is agnostic to that. So it could be vision, it could be IMU, it could be some global positioning system that appears at a lower level. So as far as our analysis go, we assume there is some sensor. We are modeling it mathematically. So it's some sensor which gives you some estimate of the relative pose of the two UAVs with some error. That's how we are looking at the problem. The other place where I mentioned UAVs and pose or state estimation was this drone racing kind of thing I was showing you with the gates and that. This is where we have done some actual experiments like this stuff. And this is all vision based. We started out with ground truth position. We have like a Vicon positioning system in the lab. So our initial policies were using that pretty heavily. But where we are now is entirely based on camera images. We are trying to estimate the position and go through these gates, which is a surprisingly hard problem. Because you see, the gates, you have to know the relative pose very accurately. If you are a little bit off, you'll collide with the gate. So at some point, it is almost worth missing the gate. Just like in slalom skiing, it's sometimes worth missing the gate if your position estimates are off, than try to go through the gate with a poor estimate. So you have to make this type of judgment call in the controller. So I think that was a long-winded answer to the first question. Was there a second one?
Yes, and I will read for the audience. So are you aware of an AV software proof that provides 99% safety assurance for lane keeping in all weather conditions? And for example, what is minimally required for sensing and control to maintain vehicle positions in all the scenarios?
Yeah, I do not. Short answer, but 99% in all conditions, right? So this all conditions is a very tricky part. The way I'm couching the problem is the way of discovering what are the conditions under which I can give you an assurance. And getting to all conditions is going to be very tricky, I feel. But I think a starting point is to say, okay, I care about this range of velocities, this range of fog, this range of, ambient light. Maybe I also parameterize the road curvature. And so I have a finitely parameterized space and range of these parameter values. Like I was showing you with the sunlight in, ambient light, you can say, this is the range of lighting that I care about. And then you can say, okay, within that range of parameterized uncertainty, let's discover what are the range in which I can give this 99% guarantee. And whether this is acceptable or not, that's going to be an engineering question, basically. Like this green set that I was showing you, is this good? I think the domain experts will have to say whether this is good enough for a product to automatically land the plane or not. Yeah.
I would personally have a follow-up on that question. So in this project that you had with Boeing, was the question to specify under which conditions we can safely land, or to tell me what is needed for a safe?
Correct. I think it's the second one. It's like the methodology. Like, how do you reason about a system like this systematically to be able to even make such a statement? And then which specific statement you want to make, whether it's 99% and what range of lighting, that will be like a downstream engineering exercise. But how do you even make a statement like that with some sort of rigor or mathematical assurance? That was the project.
Okay, that's great. And so at this very moment, there is no, let's say, target in industry to say this is what it means to be 99% safe for autonomous vehicles or for and the UAV.
So, I mean, again, does not exist in industry is a very hard thing to say, because I don't know what different companies are doing. But there are efforts to standardize what are these range of parameter values that you should care about. For example, there was a startup company, I think it's UK based, which was trying to actually do urban driving, for which actually the set of parameters you have to worry about is going to be much higher dimensional, right? You have to worry about, oh, is there a bicyclist or not? Is there a child crossing the road or not? So it's, as you move away from this, what I call structured environments like runways and highways, to unstructured environments like urban driving or inside a house, the space of uncertainty or parameters goes up a lot. So there was an effort in trying to at least define what that space of scenarios should be that you care about. How far they went and what decimal point of nines they can make a statement about, I don't know. I think my understanding of the industry is they would want to make such a statement, but it's not like the most pressing thing right now, because they have to maybe have the next product out the door and cut costs and all these types of things. Yeah.
Thank you so much. Yeah. Is there any other question? Okay, we are on time. Please join me in saying thanks to Professor.
Thank you for having me.